This video is about the various options we have to provide a clock to our microcontrollers in our custom circuits. This video is part of a series of videos about making custom circuits directly with microcontrollers and Arduino. So we will build on the previous videos by, on top of the same example simple circuit with the ATmega328P, show you in hardware how to use those options and show you as well, using the Arduino IDE, how to configure the fuses, which we will do using the mini core as we have before. Here you can see 4 different ways to provide a clock for your microcontroller in your custom circuit. The first one, which we've covered already, and here symbolized by an actual microcontroller, is the internal oscillator. The internal oscillator is built in and will work directly without the need for any external components. Now, whilst the internal oscillator might sound like a perfect solution, it has its own limitations. Specifically, there's a high degree of error to the frequency it produces, which can be off by as much as 10%. And even in good microcontrollers with good internal oscillators, it will still be off by 2–3%. Further, it drifts with temperature. So that means that in your circuit, with exactly the same chip, it can be running at one speed when it's warmer and at a different speed when it's colder. Often, this is not a problem. It doesn't really matter if things happen slightly faster than they're supposed to or slightly slower than they're supposed to, it's fine. However, when doing things like using communication protocols that require both sides to be synchronized, such as, for example, UART, also known as serial or USB, then the internal oscillator having an error might be a problem or might even make it impossible to happen. So faster serial speeds have a smaller margin of error, so in that case it will probably not work. And it will almost certainly not work with USB because of such the high speed of it and the narrow margins of error. Now, the second option doesn't have those problems. This is a crystal. A crystal is not an oscillator. A crystal is a component in an oscillator. The crystal, together with 2 load capacitors and circuitry which must be built in the microcontroller for it, will then form an oscillator. So that means that the circuit that oscillates includes something that has to be in the microcontroller. Now, most microcontrollers do have it, but some don't. So we'll come back to a solution for it in a second. The crystal is far more precise than the internal oscillator. So the internal oscillator might have an error which will be, let's say, 100,000 parts per million, so 10%, or if a good one, if you will, 20,000 parts per million. The error of a crystal is 20 parts per million. And the good crystals, often used for timekeeping, such as the 32.768 kHz ones, might have as low as 3 parts per million of error. That means that it drifts a couple of seconds every week. So, crystals are more precise, but they do require the microcontroller to support them, and they are, of course, additional components and require themselves 2 load capacitors, so they do require additional components. However, you see them very often in things like Arduino boards exactly because, well, certain things do require the precision of a crystal in order for them to be used. Serial being a good example, USB being another one. Now, next to the crystal, you see an option which is similar to the crystal, which is the ceramic ressonator. A ceramic resonator is a bit cheaper than the crystal, but it also has less precision. So the error rates of a crystal were 20 parts per million down to 3 parts per million, let's say. A ceramic resonator is more around 5,000 to 3,000. So it's somewhere in the middle in between the internal oscillator and the crystal. So whilst the ceramic resonator is useful because it is actually a direct replacement to a crystal and its load capacitors, so you can just plug it in the place as a crystal, and the extra leg that it has is what the leg that the load capacitors would have wired to ground. That's the extra leg in there. It doesn't need load capacitors. So whilst it is a direct replacement, it's not usually worth it because it's not really that much cheaper. It has a narrower range of frequencies than the crystal. The crystal, as I've said, it can go down to 32k kilohertz and up to 50 megahertz. The ceramic resonator can go a little bit up, but it can't go down to the kilohertz range. It's only megahertz area, basically. So, yeah, it's an option. It's not a common option. It might be a way of transforming a circuit which is already made and it's using the internal oscillator, and you want it to be a bit better, but the circuit is made. So this one would be an easier option to hack it, if you will. But in general, you don't really see ceramic resonators that much because they don't do enough to be worth it. Even though they're a tiny bit cheaper, it's not normally worth it. But they're an option, so here you go. Now, the last option is going to bring us back to the point I made in the very beginning. This is a crystal oscillator. It's an entire oscillating circuit with a crystal inside, all in just one package. So this thing receives power and outputs a clock signal. That is perfect, if you will, within the constraints of physics. It's a perfect square wave, about 50-50% duty cycle with the appropriate digital levels, so from the ground to the top power voltage, and with a fixed stable frequency. It does basically what the combination of the crystal and the load capacitors and the circuitry that's inside of a microcontroller would do, only that's all done in there. And the result is a clock. And that clock can be used, and that's what's going to bring us back to the first thing. It can be used for those microcontrollers, and this one here is an example of those that only have support for either receiving a clock signal or using the internal oscillator. As this microcontroller does not have the internal circuitry necessary to make an oscillator with a crystal externally. So it needs that clock. And the source of the clock can be this because, well, it's a crystal. It's going to have the same precision as the crystal itself because inside of it there is a crystal. However, this thing is significantly bigger than just a crystal. Even the SMD versions are significantly bigger than the SMD crystals. And it's 4 or 5 times more expensive. So, yeah, it's not an optimal solution, but for some situations you might need it. And there are other digital microchips which do require clocks, often enough if they have very few legs. And this can be a solution for those, although it is possible to output the clock from the microcontroller itself and then feed it on to such circuits. So, how do you use this in practice? Well, we will show you that by using the simple circuit with an ATmega328 microcontroller, which we've shown already in the first video of the series, and then on top of it we will install each different clock provision option, show you how the hardware looks, how do you configure the microcontroller to use them, and show you the things in operation. As that video already thoroughly covered internal oscillator, we will not cover that here, and instead we will start with the crystal. Further, all the knowledge around this has also been covered in that video, So we will not be covering things such as how do you make an ISP programmer, how do you wire it to the microcontroller to program it, how do you configure your Arduino IDE to the right core, how do you burn fuses, what are the fuse values, what do they mean, and so forth, because they've been covered in that video. So we will assume you already have that knowledge either from watching that video or from some other source. Before we look at the actual hardware with the crystal, we should first determine what is the value of the components that go along with it. So if you look at this diagram, and if you remember, the crystal, together with two load capacitors and the circuitry which is already inside the microcontroller, is what forms the oscillator that generates the clock for the microcontroller. So we do have to provide not just the crystal, but the two load capacitors. So what is the value for those load capacitors? Well, crystals are designed to operate with a certain load capacitance on their pins, so CL. And for this range of frequency that we would use in this kind of situation, so 1 MHz, 4 MHz, 8 MHz, 16 MHz, and so forth, the typical value for the load capacitance for which a crystal has been designed is 12.5 picofarads. Now, if you go and you get a crystal from a generic supplier that doesn't even mention load capacitance, it's going to be almost certainly 12.5 picofarad. If you go to a specialist electronic supplier, then you can actually choose, because crystals for these frequencies have been made and are available that expect different load capacitances. So if you go and get one from there, either you specify you want a 12.5 picofarads and just do it like this, or you get a different one and you do the maths and you use that one. So, talking about doing the maths. So how do you determine the values here? Well, first thing is they should be balanced. Both sides of the crystal should be balanced. So we can simplify this by saying, okay, both load capacitors have the same value. Now, if you temporarily put on the side the C-stray, you can see from the formula that to get the specific load capacitance for the crystal, then the capacity of each capacitor should be twice as much. So for those 12.5, load capacitors should be 25 picofarads each. Only they shouldn't, because there's the C-stray in there. So what's the C-stray and why do we care? Well, all circuits, elements of the circuit, have a tiny amount of parasitical capacitance. So that C-stray is also known as the parasitical capacitance. And, two lines going along each other in a PCB or on a breadboard, they're like a mini capacitor. Each line is a plate on a minuscule, tiny capacitor. And similarly, the pins of the microcontroller and so forth. And in fact, circuits also have parasitical inductances and parasitical resistances. They're also tiny things, and those last two don't really matter here, but the parasitical capacitance does, because the values of those things, even if you keep the lines from the crystal to the microcontroller and to the load capacitors short, are actually in the range of the load capacitance that the crystal expects. So they do actually have an impact here. I'll give you an example. If you start by saying, okay, the circuit already has a parasitical capacitance of 2 picofarads, then your load capacitors cannot be 25 picofarads anymore if you want to provide the exact load capacitance that the crystal expects of 12.5. Why? Because 25, that's indeed 12.5, but then there's the additional 2, so that's actually 14.5. So what happens in this situation is that your load capacitors have to be smaller to take in account that stray capacitance. So in that situation of the 2 picofarads of stray capacitance, they actually have to be 21 picofarads each, because the result is going to be half as much, so 10.5, to which you add the 2 picofarad stray capacitance, and that sums the 12.5, exactly what the crystal expects. So, How do we determine the stray capacitance? Well, you don't. You can only really do it if you have very specialized equipment. And it only really makes sense in a PCB which has been designed. And it's not going to change. It doesn't really make sense on a breadboard where the pins you actually use, if you move the whole thing a little bit to the side, you might have different parasitical capacitance. So what you do is you eyeball it. So what's the downside of eyeballing? Well, you might be off. You probably are going to be off. Maybe not too much, but you are going to be off. So what's the problem of being off? Well, in this range of frequencies, as long as you're not too off, like crazy off, it's still going to oscillate, but the frequency is going to be pulled away from the specification. But it's not too bad. And yeah, eventually they will not oscillate anymore. And it's easier to get problems if you do it too much than if you do it too little. But there's quite some range for maneuver. Now, if you were using the crystals for, say, 32.768 kilohertz, which are used in timekeeping, those are much more sensitive. So in those cases, it's a lot harder to get away with it. But the megahertz ones, you can get away with crazy stuff. So don't worry too much. And this is why often if you look at videos and say, oh, this is how you use a crystal. And some people go like, oh, use a 20 picofarad. And other people say, oh, use a 22 picofarad and 21 picofarad and so forth. Some people don't even use a load capacitor, right? And they get away with it because there's so much margin for maneuver there. But as I said, you're going to have some frequency error in there. Here you can see our ATmega 328P wired with the crystal. Notice there are two load capacitors. So there are two legs in this microcontroller which are dedicated to providing the other part of the oscillating circuit that goes along with the crystal. And if you look in your pinout diagrams in the datasheet or in the pinout diagram from the mini core, you will find them named something like XTAL1 and XTAL2. Now these things are, well, it doesn't matter the orientation you put the crystal on them because it's the same from both sides. So the crystal gets wired into those pins. And they're right next to the power, which is why you see this thing a little bunched up. And the other sides so the pins of the crystal are via the load capacitors wired to ground. That's basically it on this side. On the other side, I will in a moment explain how you configure it, but it's also pretty simple. If you've seen our previous video on how to do it for the internal oscillator, it's the same thing and just choose something different there. And well, it's working, right? I'm going to show you how it is actually the crystal working, not the internal oscillator, very easily. So take this off. Take the crystal off without taking anything further off, right? That's it. It's absolutely fine. And it's not working. So, which makes sense. There is no clock for this microcontroller. And it will not, some more modern ones might, but this one will not fall back into using the internal oscillator as default, so it doesn't run. Now, I'm going to show you how you use a ceramic ressonator here, because it is a direct replacement to the crystal. So first, let's just take the power off, and we need to take the two load capacitors off, and well, there are three legs here. The side ones are as if they're the crystal legs, and the third middle leg, which I already have extended because it's gonna go to there, it's as if the other legs of the load capacitors. It goes to the ground. So that's it, you just install it. making sure, of course, that it goes to ground, not VCC. So, because that would be not nice. Turn the thing on, and there you go. So, yeah, that's it. And notice I I didn't need to reconfigure the fuses on the microcontroller. So, yeah, you just take one, put the other one in, and it works. And as I said earlier, ceramic resonators are a bit cheaper, but they have quite a lot less precision. So, the way you configure your microcontroller to run with an external crystal is very much the same as you would configure it to run with the internal oscillator. You have your Arduino IDE with the mini core, and in the tools menu you have the options you set. So once you set your board to being the correct one, which it already is, but you can see here from the mini core, you then have all the other tools. And everything else here works pretty much the same as in our last video. And you set it the same as in our last video. So don't forget the port, don't forget to have the programmer correct, that's all the same. And you can see here it's set to internal 8 MHz. Only now we're not going to set it to that. We're going to set it to the crystal, so that's an external one. Further, we're going to set it to the speed of the crystal we have out there. And in this case, I have an 8 MHz crystal outside. So I'm going to set it to external 8 MHz. At this point, with all the rest done, which was already done, I can burn bootloader, and this will burn the fuses of the microcontroller so that it starts using the crystal. And now that I have this, I can just use the normal upload procedure. Now, there is something very important here. The microcontroller isn't actually configured for a specific crystal speed, and the microcontroller cannot determine the speed of the crystal. The speed of the crystal is a property entirely of the crystal. So if you put an 8 MHz crystal there, then the microcontroller is going to be running at 8 MHz. It's not going to be running at whatever speed it decides it's going to be running at around that. No, it's going to be what the crystal says. That's the whole point of the crystal. They set the speed in a very precise way. So the microcontroller, when you go here and you choose tools and you choose here an external 8 MHz, and then this gets put into fuses via burn bootloader, you're not actually saying it's going to be an 8 MHz crystal. In this specific case, for example, there is a range of crystals from 8 MHz above. And that's what's there in the fuse configuration. There's a crystal outside which is 8 MHz above. And that's because certain characteristics of the internal circuitry that oscillates with the crystal are adjusted to better match certain ranges of crystals. But it says nothing about the speed. If I had a 16 MHz crystal in there and I chose here the 16 MHz and I burned the fuses, guess what? It would be the exact same fuses. Because, yeah, it's any crystal in this range. So why is this here, right? Why is it not some kind of range? Well, this is used also during compile. So the first thing, maybe most important, and I'll explain why. You should have it set to the same configuration from here onwards if you're using this microcontroller. And if you change microcontrollers, you have something else that's running at 16, okay, then you set it to 16, right? You don't need to burn the fuses. The crystal defines the 16, but you do need to do it here because of compilation. Why? Well, say you want to do millis, right? In the Arduino libraries, you want to calculate the millisecond for making of a delay. You have here in the blink, there's a delay that says 1000 milliseconds, right? So the thing has to know what is 1 millisecond, how long it takes. Guess how the thing knows it? Well, when you compile it, you pass a define, it creates a define inside everything, even here you would have it, which called f_CPU, all big case, and it's the number of cycles per second. So here in tools, when I say I'm going to run an external 8 MHz crystal, this causes that on build time, which is why this should be set and remain set correctly on build time, that f_CPU is going to say 8 million. But if I select 16, that's going to be saying 16 million. And that number is then used to calculate, for example, for millis and delay, there's a timer, and it calculates how many cycles the timer should run before it basically notifies you that a millisecond, you being the Arduino libraries, that a millisecond has passed. Right? So if you have 1,000 here in a delay, that means there's gonna be 1,000 such notifications. It's roughly like that it works, 1,000 such notifications. Now, if your crystal makes it 8 megahertz, but the number I have selected here during compilation is external 16 megahertz, so that means that 16 million is the number of cycles the Arduino libraries are being told run per second in this microcontroller, is going to basically do the maths based on that assumption, which is wrong. So what the thing's going to do is it's going to basically, from 8 million to 16 million is twice as much. So it's going to be telling the timer that it needs to run twice as many cycles. And the result is that this delay here, which was supposed to be 1,000 milliseconds, is 1,000 times those wrongly calculated milliseconds, which are now twice as long, because they were calculated for 16 million operations per second, but the thing is running at half the speed. It's running at half the speed, it means it waits twice the time. And that's the reason for this. And this is very important when you switch microcontrollers, or even in general, you're playing around for some reason, you change this. It's very important that what you have selected here matches the speed of the crystal you have in there. Here you see the circuit with an external oscillator. So the ATmega 328P with an external oscillator. Now, you can see that the external oscillator is just being fed power. Just like the microcontroller is being fed power, the external oscillator is being fed power from the same rails. And it has a single output, which is this white line, and this is the clock signal. So it is an entire self-contained circuit, and if I had other uses for this clock signal, I could use them there. And because, it's the function of the whole thing. The microcontroller has to be configured to take in as the clock signal an external clock, and in fact I'm using pin XTAL1, which would be otherwise one of the crystal pins, to receive the clock signal. So all that circuitry about driving a crystal and making an oscillator is disabled, and this signal is being routed elsewhere, directly into the internals of the thing. And this is how it works. I'm going to show you that this is in fact working by doing something quite simple. I'm just going to take it off, right? There you go. No clock signal. And you can see it's actually stopped mid-blink. The microcontroller is not being clocked. It's just not getting any up and down square wave cycles. So it doesn't do anything. It's completely frozen now. And restore it by wiring it back to the same pin. There you go. So, why use an external clock signal for this one? Well, for this one it doesn't make that much sense. But there are, as I said before, there are microchips and even microcontrollers which do not take crystals. They only accept external clock signals. In some cases they have internal oscillators, but other things like waveform generators, they don't even have that. They require an external clock signal, and you have to provide it somehow. So, this little package, well, this big package, really, is a way of generating such a clock signal.